Okay, folks, I have 2 minutes past, so let's go ahead and get started. I don't think we have too much in the way of logistics to discuss, but I wanted to continue this discussion that we had on Monday about options for exam number 2. Let me share screen for a moment because I posted about this on Canvas, and this is where I'd like to get your feedback. So when you log into Canvas, you should see something like this. I think this is the student view. I posted this under announcements. So if you go to announcements, you will see this thread, discussion and consensus about midterm 2. If you click on that, you will see my summary of what we discussed in class on Monday. And what I've done is I've opened this up for liking posts and for posting your own comments in reply. So what I did was I posted a separate comment for each of the options that we discussed. So option A being proceed rigidly with the schedule, and this is what that timeline might look like. Option B, which means delay by 1 class period. That would buy us all a little bit more time, but wouldn't change the schedule crazy much. Option C, which was proposed in class, is to hold the midterm as a take-home. So here's sort of a discussion of the implications of that. That would free up more time to go over lecture material, and it would mean that you guys would have some chance to practice the material on the midterm and still have another grade that would help dilute individual grades that you had for, say, the midterm 1 or the final. And then option D would be just cancel midterm number 2 altogether. So what I would ask you to do, if you've not already done so, is to go to this thread and weigh in with your opinions so that I have a good sense as to what the class wants to do. You can vote, quote unquote. You see down here in the bottom left corner, there's a thumbs up for liking a post. If you click that, then I will count that as your vote for what you want to happen. You're also welcome to post a comment about options that you like or dislike for whatever reason, questions that you might have. We've had some questions already. But I wanted to centralize the discussion in one place so that I can get a sense as to what the class wants to do. Thus far, it seems like we've got nobody wants to pursue option A, which is okay with me. We have 1 vote for option B. We have 1 vote and a couple of comments supporting option C. And right now it seems like the favorite is canceling the second midterm altogether. So that is up to you. And I reserve the right to make the decision myself, but I want to know what you guys want to do so I can factor that in. So if the class strongly prefers to cancel the midterm altogether and just push it to the final exam, then I would be okay with doing that. So if you have not already gone to Canvas and weighed in on what you would like to happen, please do so either right now or as soon as possible so that in the next day or so, I can get a consensus as to how the class wants to move forward starting next week. Any questions, concerns, or other discussion that you guys want to have about this now?
I have one.
Yes, sir.
So having a take-home midterm, you mentioned that there wouldn't be enough time for a regrade opportunity. Would we still do a sample/practice exam before the take-home?
I hadn't decided, to be completely honest. So if we resolve this and that's what you guys want to do, I could try to do that. I don't know if we would do it in class. I don't know. I hadn't decided. What is your feeling on that? Do you think that if this is a take-home exam, you've got a whole week to work through it and you've got similar problems on the homework? Do you need a sample exam to help guide through how to do that kind of stuff? Would you want to do that in class? Is that something that I should just post online for your own review? How would you want to see that handled?
I don't know. I really liked the sample exam when we did the normal exams, although I see how the format would make a pretty big
right. If we're going to do an exam in class, then I would definitely do the sample exam. If we're going to do it as a take-home, I would like to be able to do the sample exam. If we can work out a timeline that makes that feasible, I would be open to doing so. But this was not something that I had planned on myself, so I'm still sort of working through the implications of what that might look like. So I'm open to that idea, and I think it's doable.
Okay.
Other thoughts or concerns? Okay, if not, then I will leave this here for now. Like I said, you guys are welcome to go weigh in on that at any time, but please do so as soon as possible so that I can make a decision about how to move forward in the next couple of days. Okay, any other things that we should discuss before we dive into physics for the day? Okay, so the last couple of weeks we've been discussing scattering theory in many different respects. The basic setup of scattering theory was as a boundary value problem on the wave function for the time-independent Schrodinger equation. To remind you, we were solving for the boundary conditions at r goes to infinity, consisting of an incoming plane wave, usually chosen along the z-axis, u the I k z, and an outgoing spherical wave, u the I k r. Yes, right. U the I k to z and e to the I k r, where this amplitude is f of theta and f of phi. This is referred to as the scattering amplitude. The scattering amplitude is what determines the scattering cross-section. Much like a wave function, the observable is equal to the amplitude squared. So this is some f star f analogous to psi star psi for the probability that you observe. We talked about how to calculate the scattering amplitude f. The simplest way and the one that you will need to be able to perform under pressure is the calculation under the Born approximation, which is just lowest order in perturbation theory, which is just given by a coefficient and the Fourier transform of the potential. So the picture of the diagrams that we've drawn for this was that your incoming momentum absorbs momentum h bar q from the potential and goes out with p final. And that's why you have something proportional to the Fourier transform of the potential. And then last class, we finished the discussion about how to go beyond the Born approximation, that this is just the first term in an infinite perturbation series, and that one can systematically construct higher order calculations using Green's functions, and that these things are so systematic that they naturally can be enumerated in terms of Feynman rules in momentum space to explicitly calculate any order in perturbation theory. So the topic that I want to cover today is the last new material for scattering theory, which is about scattering lengths and phase shifts. Before I dive into this new discussion, I wanted to wrap up this conversation about the Born approximation and beyond the Born approximation by saying a few words about when the Born approximation is a reasonable approximation and when it would be invalid. So let us recall that the Born approximation refers just to first order in perturbation theory. So in order for perturbation theory to be a good approximation, your coupling constant needs to be small, or the correction coming from the perturbation needs to be small. So in terms of my incoming plane wave is my unperturbed state, and the presence of the potential is what generates the scattered wave. This sense that your perturbation should be small means that your scattered wave should be much smaller than your incident wave. So one way to estimate this is to describe the contribution of this near the origin, where the potential is the strongest. Obviously, if you go far away from the potential, then the effect of the potential looks smaller. But one way of quantifying the strength of the potential is to look at this ratio at the origin, at r equals 0. So if I write down the expression for the scattered wave in first order perturbation theory, we said that, let's see, psi of r is minus m over 2 pi h bar squared integral d3r. So this came from the Green's function. And we found that the Green's function was e to the minus I k r minus r prime, absolute value r minus r prime, potential v of r prime, and then we had the incident wave at r prime. So if I take this and I divide by the incident wave, then I'm just forming this ratio. And if I want to consider this ratio at the origin, then I will take the Green's function, and in here I will set r equals 0. And now this is evaluated at r equals 0. So the ratio that I want to consider to decide how good the Born approximation is is absolute value psi scattered of 0 over psi incident of 0. And this is m over 2 pi h bar squared, absolute value integral d3 of r prime. Let's see, e to the I k r prime over r prime, d of r prime, and then psi incident of r over psi incident of 0 just cancels the prefactor, and I get e to the I k z, where z is r cosine theta. I guess this would be z prime in these prime coordinates. So you can do this integral, so is this absolute value? Let's see, so if I break this up and I do it in spherical coordinates, 2 pi h bar squared, this is absolute value integral dr prime, 0 to infinity, r prime squared from the measure, integral d cosine theta from -1 to +1, integral d phi from 0 to 2 pi, the I k r prime over r prime. Let me consider for simplicity the case when the potential is spherically symmetric. So let's take this to be v of the magnitude r prime. And then I have e to the I k r prime cosine theta. Absolute value. So the phi integral is trivial. I just get a factor of 2 pi, which gives me m over h bar squared, integral 0 to infinity dr prime. I've got r prime squared over r prime. That cancels one of the r primes. I have e to the I k r prime, v of r prime. When I integrate d cosine theta from -1 to 1, I get 1 over I k r prime, e to the I k r prime minus e to the minus I k r prime. That's the value. So what I get is psi scattered over psi incident is, all right, absolute value of the I is 1. I pull out the factor of k, and then this r prime cancels the other r prime. So I get m over h bar squared k, absolute value 0 to infinity dr prime. Now I just have e to the I k r prime. This difference that's left is e to the I k r prime minus e to the minus I k r prime, e of r prime. And I can write this difference as 2i sine k r prime just to make it a little bit more compact. So my expression is 2m over h bar squared k, integral 0 to infinity dr prime, e to the I k r prime sine k r prime. And I want this object to be much less than 1 if the perturbation is small. Sorry? Potential. Oh, yes, the potential. Thank you. That's important. Remember h bar squared k? Yes. So this is my criterion for the validity of the Born approximation. This is really more of a test of, is the perturbation small and does this justify truncating the perturbation series at all? If this object is much bigger than 1, then you shouldn't use perturbation theory at all. If this is much smaller than 1, then the Born approximation is good, but the next to leading order approximation is better. But you have the ability to stop the series at any point you choose. Okay, so if this is my criterion, it's useful to consider this in 2 different limits, the limit of high energies and the limit of low energies. So let's take 2 cases, the high energy limits. So formally this would be k goes to infinity, or really more like k r prime much greater than 1. or I can consider the low energy approximation, which would be K goes to 0, or really Kr prime much less than 1. So first, let's talk about the low energy asymptotics. If I take the low energy, and I take K to be small, K is sitting down here and K is sitting here in the exponential and in sign. So let me approximate them both by their lowest orders. So I have this ratio is psi scattered over psi incident is, let me put approximately, m over 2 pi h bar squared, m over h bar squared k. And then inside here, I have integral 0 to infinity, dr prime. I approximate the exponential as 1. I approximate sine of theta by theta, k r prime, d of r prime. I want this object to be much less than 1. So k cancels the k. And I get just the first moment of the potential. So I get something like, oh, and there was a factor of 2. 2m over h bar squared, 0 to infinity, dr prime, r prime, d of r prime. The details of this integral are going to depend on the potential, but this is some sort of average. This is telling you after the integral is finished, this is some measure of length squared and then some value of the potential. For some, let's say, range R naught of the potential and depth V naught of the potential. And really, I guess this could be positive or negative. I don't really care that much for this estimate. This is really just based on dimensional analysis. There could be factors of a third or a half or whatever in front of this, but this is some dimensionful integral that tells me the length scale associated with the potential squared. I've got length and another length, and I've got the magnitude of the potential itself. So what is the criterion if this is much less than 1? I have 2m over h bar squared, r naught squared, v naught, much less than 1. This tells me that the potential must be small in comparison to h bar squared over 2m, 1 over r naught squared. This object looks familiar. This looks like the prefactor in front of the kinetic energy. And this is the typical length scale. So this is the energy of the uncertainty principle of a particle which is inside a length r naught. So this is the uncertainty kinetic energy. Or maybe you could call it the 0 point energy. Of a particle confined to a range R naught. So essentially what this is telling you is the potential needs to be too shallow to admit a bound state. It means that your plane wave is coming in and you've got a potential whose depth V naught is so small that if you try to squeeze a wave inside of it, the ground state for this thing would have energy h bar squared k squared over 2m, which is greater than V. Right? If this thing is so shallow that you can't actually get the particle trapped inside, then it looks like the plane wave just comes in and bounces off. There's not a strong interaction with the possibility of a bound state inside. So the physics associated with this is that the potential is too shallow or weak to allow a bound state.
So the potential of 1 over r square, or
Sorry, say again.
if for example v of r prime is 1 over r Coulomb potential.
Yes, yes. So 1 over r is a very singular example because as we saw, the range of the Coulomb potential is infinite. So if this thing were 1 over r, then this integral would not be well behaved. And so in that case, the object would have infinite range. So the Born approximation is never a particularly good description for the Coulomb potential because it has a very long range.
For example, VFR is 1 over R cubed or more.
Yes, that's right.
That's what.
That's right. Yeah. So if this decays fast enough at long distances, then you can associate a range with it. The Coulomb potential with 1 over R is right on the boundary, right? Integral of 1 over R is a logarithm instead of something which is convergent when R goes to infinity. Yeah, so this assumes that the potential is decaying fast enough for large R that you can actually do the integral and get something finite with finite range. So Coulomb potential doesn't work very well for this, but the Yukawa potential works better if you had some mass that gives it a finite width. Right, very good. So for low energies, the approximation is that the potential is weak in comparison to the confinement energy of a particle inside the potential itself. In the high energy approximation, I take the opposite limit. I say the phase is very rapidly oscillating. The sine function is also rapidly oscillating. So what do I get? Here I have e to the ikr and e to the ikr. These guys together are very rapidly oscillating. This is e to the 2ikr. But this one, e to the ikr and e to the minus ikr cancel each other. So this term is not rapidly oscillating and does not average to 0. This term does. So in the high energy approximation, I'll go back to that sine form. This ratio psi scattered over psi incident is something like m over h bar squared k integral 0 to infinity dr prime. And then if I put this back together, I have e to the 2 ikr prime minus 1 e of r prime. And so my approximation is to say, as k goes to infinity, this phase is rapidly oscillating and averages to 0. And so I only keep the 1. And so what I get is something like m h bar squared k absolute value 0 to infinity dr prime v of r prime. And I want this to be much less than 1. This object is just the average value of the potential. So this is some range R naught times V naught, the same kind of depth. So, but now this K doesn't go away. I want this object on the left to be small in comparison to 1, and this denominator is going to infinity. That looks pretty good for me. So another way to write this is to say that V naught needs to be much less than H bar squared over M K R naught over R naught squared. So this looks like what I had before. H bar squared over m r naught squared. That's the confinement energy of a particle trapped inside the potential, but this is times a large factor, much greater than 1. So that means this approximation is always good if k is going to infinity, Coulomb potential aside, which is a special case. But if the energy is high enough, then this is always a good approximation. Born approximation may fail at low energies if the potential is not shallow enough. But if this is true, this is automatically true. So a couple of points to state explicitly about this. The high energy criterion is always valid at sufficiently high K. At high enough energy. So I need V naught much less than H bar squared over M R naught squared times K R naught, with this thing becoming large. And the second thing is, if the low energy criterion is satisfied, then the high energy criterion is always satisfied everywhere. If low energy criterion is true, then it is true at all energies. Because if I have V naught much less than H bar squared over M R naught squared, This object is also automatically much less than h bar squared over m r naught squared times k r naught. So if this inequality is satisfied, which is the low energy criterion, then this inequality is automatically satisfied, which is the high energy criterion. So the point that I want to emphasize here is that the Born approximation is a good approximation at high energies. It may or may not be a good approximation at low energies, depending on how big the potential is. So this framework that we've been building thus far is a pretty good description for relatively high energy scattering. It may fail at low energy scattering. And low energy scattering is where this partial wave expansion that we will discuss next is more advantageous. All of this also needs to go within the caveat that we are still dealing with non-relativistic scattering. So when I say when the energy is high enough, once the energy starts getting relativistically high, all of this changes. So don't take this literally and run to the LHC with it. The picture is going to change and you have to do non-local, non-instantaneous relativistic perturbation. Okay, any questions about this? Okay. So the partial wave expansion. Thus far, the setup that we've been using to describe scattering theory has been with an incoming plane wave, e to the I kz, with momentum h bar k in, scattering on some kind of potential, generating an outgoing spherical wave, which we ask about in a particular direction. So we have e to the I k r over r with momentum h bar k phi. The partial wave expansion is a reformulation of this completely in terms of spherical waves. So I have the ability to take this plane wave and decompose it in terms of spherical waves. Decompose into spherical waves too. And that's kind of useful because then that means that the problem looks like spherical wave in, which is e to the minus ikr over r, and spherical wave out, e to the plus ikr over r. The spherical waves have well-defined values of angular momentum. So this is a useful way of describing the process one angular momentum mode at a time. So this is used for describing independent scattering of each YLM angular momentum mode. This is especially useful at low energies. The reason is that at low energies, only a few angular momentum modes participate in the scattering. That's easy to see from this plane wave description. So if I imagine my target is some hard sphere, and I've got my plane wave coming in, which is made up of individual particles, let's say. These guys are coming in with momentum p equals h bar k. Which ones actually hit the target and participate in the scattering? If the target has a characteristic range, if this has some distance scale r naught, then the ones that are far outside of r naught miss the target completely. So these do not participate in the scattering at all. The ones that do participate in the scattering are the ones that are at distances less than r naught. And those carry specific amounts of angular momentum. So I can calculate r cross p and ask how much angular momentum is being carried by this particle that's going to hit the target. So the amount of momentum of the particles that will hit is L equals r cross p. In this case, the momentum is h bar k along the z-axis, and this r cross p couples to that perpendicular component r naught. So this is r naught h bar k, or let's say r perp h bar k. And since I know that scattering only takes place for r perp less than r naught, then this means that the amount of angular momentum which is participating in the scattering is less than r naught h bar k. And if I think about this in terms of quantum numbers, quantum modes, and I write L is something like h bar L, I'm not going to worry about specific factors, then this tells me that the angular momentum modes that are participating are something which is less than the range times the momentum k. So few angular momentum modes will participate in the scattering if the range is short or if the energy is low. So if the range R naught is small, or the energy h bar squared k squared over 2m is small, i.e. k going to 0, then only the first few angular momentum modes will participate in the scattering. So this partial wave description is something that you often encounter for low energy scattering, something like cold atom physics, where you have particles bouncing off each other with low energies that do not necessarily resolve all of the complicated structure inside. You can have all this multipole detail inside the potential, but if the energy is low enough, the incoming particle does not resolve it. Its wavelength is too long to see the detailed structure inside. And in that case, you just see the lowest multipole moments. You see L equals 0, S wave, L equals 1, P wave. And those lowest couple of scattering coefficients are easily calculable in terms of the spherical wave scattering with definite angular momentum. So for simplicity, we will consider the case of a spherically symmetric potential. If that's the case, then I don't need all of the YLM spherical harmonics. It's enough just to take M equals 0, the completely rotationally symmetric ones, and then I just have, or the azimuthally symmetric ones. And then I only have the Legendre polynomials. So let's consider only a spherically symmetric potential. V of R. And so then we only need Legendre polynomials. That is YL0, which is proportional to PL of cosine theta. Another thing that's very nice about this is if the potential is rotationally symmetric, then that means that operator is a scalar. It does not generate any angular momentum of its own. So if the potential is spherically symmetric, then each angular momentum mode scatters independently. You don't have anything that comes in with L equals 0 and goes out with L equals 1. Each L mode scatters independently of the other one. So you've got S wave scattering, L equals 0 in, determine L equals 0 out, L equals 1 in determines L equals 1 out, but there's no mixing of the two because the operator here carries 0 units of angular momentum. If V of R is scalar, then there is no mixing of modes. Okay. Is the motivation clear? We have the Born approximation, which is a pretty good description for high energy scattering. This partial wave decomposition is a good approximation for low energy scattering for these reasons. All right, so to actually use this in practice, we have to pull in some properties of special functions, specifically the spherical Bessel and Neumann functions. So the goal to get us started is going to be expand the plane wave e to the I k z in terms of spherical waves. So first, we need a good basis for describing the spherical waves for arbitrary angular momentum. So we need to look at the solution to the free particle Schrodinger equation. So that is minus h bar squared over 2m e squared dr squared plus h bar squared L plus 1 over 2m r squared. Radial probability amplitude u of r is h bar squared k squared over 2m u L of r. And this is related to the full wave function psi of r, theta, and phi by it is UL of r divided by r is the radial piece times the spherical harmonics, YLM of theta and phi. So we want to solve the radial equation for a free particle like this. Let's look specifically at the solution for L equals 0. For L equals 0, the radial equation is simple. I have minus h bar squared over 2m d squared u dr squared equals h bar squared k squared over 2m u. Cancel the coefficients, and I just get u double prime is minus k squared u. This solution is trivial. This has sine and cosine solutions. So u for L equals 0 must go like sine of kr or cosine of kr. So this means that the wave functions which come out of this have two independent solutions. So you have sine kr over r, and conventionally we talk about it with a negative sign, negative cosine kr over r. So this is the solution for L equals 0. Let me observe one property of these two functions. That property is that as r goes to 0, the sine of kr over r is finite. Finite as r goes to 0, because sine of kr becomes kr in the numerator, which cancels the r in the denominator. You get something finite. Cosine, on the other hand, diverges. I get 1 in the numerator and 0 in the denominator. Divergent as r goes to 0. So the S wave case, L equals 0, is trivial to work out. The answers are just sine kr over r and negative cosine kr over r. The solution for finite L is highly non-trivial, and we don't have time to derive it all here. The answer can be constructed in terms of operators acting on these lowest order solutions. And these define the spherical Bessel and Neumann functions. L greater than 0, the solution are the spherical Bessel functions and Neumann functions. So the spherical Bessel functions, little jl of x, are defined to be negative x to the power L, a differential operator 1 over x, d by dx, L times acting on the lowest order solution, sine x over x. The spherical Neumann functions, NL of x, is something similar. This is negative x to the L, 1 over x, d dx, L times, acting on the lowest order solution, negative cosine x over x. So because the Bessel and Neumann functions are constructed out of the lowest order sine and cosine kr over r, they retain these properties about their behavior at 0. So the spherical Bessel functions are again finite as r goes to 0. The spherical Neumann functions are divergent as r goes to 0. One other property that we will need about the general Bessel and Neumann functions is their large argument asymptotics, because we will need to match onto boundary conditions when r goes to infinity. So the other piece that we will need is the statement that JL of KR in the limit r going to infinity behaves like sine kr plus L pi over 2 over kr. Make sure I'm pulling that right. Minus. And the spherical Neumann function is NL of kr as r goes to infinity behave like negative cosine kr minus L pi over 2 over kr. So this is what the general solutions for the free particle with definite angular momentum look like in 3 dimensions. They are the solutions to the free particle equation. They are built out of the elementary sine and cosine spherical waves. The sine is the root of all of the higher order spherical Bessel functions. The cosine is the root of the higher order spherical Neumann functions. And in the large distance asymptotics, these reduce back down to their elementary forms with a phase shift that depends on L. Okay, so this means that the general solution can be written as a linear combination of these functions. The general solution for a free particle in 3 dimensions written in spherical coordinates is that psi L of r and theta, if this thing has m equals 0, it's independent of the azimuthal angle, is decomposed into a sum of those radial wave functions, sum over L equals 0 to infinity, a sub L spherical Bessel function of kr, plus b sub L spherical Neumann function of kr, times the Legendre polynomials, EL of cosine theta. If this were the more general case where the wave function could contain azimuthal dependence, then you would potentially modify, I don't think you would modify the radial equation. I think it would still be the Bessel and Neumann functions, but you would have the full spherical harmonics here. But for the purposes that we'll be using it for, we will only need the Legendre polynomials. Okay, so the goal was to expand the plane wave in terms of this basis. The plane wave is a valid solution to the free particle equation. So we know that e to the ikz must be expandable in terms of the spherical Bessel and Neumann functions. So I must have e to the ikz, which if I write it in polar coordinates is e to the ikr cosine theta, must be expressible as a sum from L0 to infinity, AL spherical Bessel function of kr, BL spherical Neumann function of kr, times Legendre polynomial of cosine theta. And what I want to do is find these coefficients. One thing that I can do immediately is rule out the contribution from the spherical Neumann functions because of their behavior as r goes to 0. The plane wave is finite when r goes to 0. So it cannot have any contribution from the singular Neumann functions when r goes to 0. That is true in general. Any function which is regular or finite as r goes to 0 does not get a contribution from the Neumann functions. So now I just have one set of coefficients to figure out. E to the ikr cosine theta is sum over L, AL, spherical Bessel function of kr, Legendre polynomial of cosine theta. It's easiest to think about what to do next if you consider this in terms of a vector space. These functions are a vector space of their own, and the Legendre polynomials are a basis for that vector space. They are, in fact, an orthogonal basis for that space. So if this is some vector decomposition, and I want to know what is the coefficient of this vector in that basis, I need to take the inner product and use the orthogonality to do that. So we need to use the orthogonality of Legendre polynomials. The Legendre polynomials are orthogonal, but they are inconveniently not orthonormal. So there's a coefficient that shows up. You integrate -1 to +1 d cosine theta, PL of cosine theta, PL prime of cosine theta. What you get is 2 over 2L plus 1 Kronecker delta, LL prime. So this is the definition of the inner product on the Legendre polynomials. They are orthogonal because you get a Kronecker delta of L and L prime. They are not orthonormal because you get a constant which is not 1. Still, using that, you can project out the coefficient that you want. So if I have e to the I k r cosine theta equals sum over L, a sub L, JL of kr, PL of cosine theta, to use that orthogonality, I need to multiply by a different Legendre polynomial PL prime and integrate. So if I integrate d cosine theta from -1 to +1, e to the I k r cosine theta, PL prime of cosine theta. Then this is equal to, on the right, sum over L, AL, JL of KR, and now I have the integral d cosine theta, -1 to +1, L of cosine theta, L prime of cosine theta. This inner product over the Legendre polynomials lets me use the orthogonality property 2 over 2L plus 1, delta L prime L. The Kronecker delta kills the summation and picks out just the specific term that I want. So this is 2 over 2L plus 1 prime, AL prime, JL prime of KR. So this effectively lets me solve for the coefficient that I want by performing a specific integral over the plane wave. So this is what determines the expansion of the plane wave, e to the I k z. Well, let me just write it this way. A sub L is equal to 2L plus 1 over 2 Bessel function, JL of KR, times the result of that integral, d cosine theta from -1 to +1, e to the I KR cosine theta, specific Legendre polynomial PL of cosine theta. So if I can do this integral for any L, then I can find the coefficient for any L. Doing that is a non-trivial exercise that we do not have time for here. But it's doable if you write down the general form of the Legendre polynomials. You can write them in terms of derivatives of basic polynomials. You can do the integral. It's all straightforward enough to do, but it's more time consuming than we have time for. If you do this, the final answer is A sub L is equal to I to the power L to L plus 1. And if I write that I to the L as e to the I pi over 2 to the L, then this is 2L plus 1 e to the I L pi over 2. So this is the answer that we needed to determine this basis expansion, and then convert the problem from plane wave into spherical waves into spherical waves. So the final expansion that we needed is e to the I k z is equal to sum L equals 0 to infinity. My coefficients are 2L plus 1 e to the I L pi over 2 Bessel function KL of JR times Legendre polynomial PL of cosine theta. So this is the general decomposition of the plane wave, that's our initial condition, into Bessel functions, which have contributions from spherical waves in and spherical waves out. Okay, so we want to match this onto the asymptotics of the scattering problem. Plane wave in and then spherical wave out, which we now convert into spherical waves in and spherical waves out. So let's consider the r goes to infinity asymptotics of this plane wave. So if my psi incoming is equal to e to the I k z, For simplicity, I'm going to take that prefactor to be 1. We've been calling, to be 1. We've been calling it A before. It's just going to make things more complicated if I keep it around now. If I take this thing and I take the limit as r goes to infinity, then that lets me use the r going to infinity asymptotics of this Bessel function, which we said were a phase-shifted sine kr over r. So this looks like sum L equals 0 to infinity, 2L plus 1, e to the IL pi over 2. My Bessel function then becomes sine of kr minus L pi over 2 over kr, EL of cosine theta. Yes. And so now I'm going to decompose this sine function into a pure spherical wave in and a pure spherical wave out. That sine is equal to e to the I kr minus L pi over 2 minus e to the minus I kr minus L pi over 2 divided by 2I. And this one is the outgoing spherical wave e to the I kr. This is the incoming spherical wave e to the minus I kr. So when I put all of this together, I have sum over L, 2L plus 1. I now have an overall factor, 1 over 2I kr. And let me pull the r and put it together with the spherical waves. And let me also distribute this phase factor. I've got e to the plus I L pi over 2, which cancels this phase, but it adds constructively with this one. So what I get is e to the I kr over r minus e to the minus I kr minus L pi over 2 over r times L of cosine theta. Did I get it right? So I should have over, not over 2. Thank you. Yeah, this combination was plus I L pi over 2, and I've got another plus I L pi over 2 here. So I get plus L pi at the end. Okay, so the point of all of this is that now asymptotically I can decompose my plane wave into something that looks like purely outgoing spherical waves. And a purely incoming spherical wave. Now we're finally in a position to formulate the matching of the boundary conditions. Everybody with me so far? Any questions on this? This is mostly an exercise in special functions with the spherical Bessel and Neumann functions. The main point was establishing this decomposition so that then we can perform the translation between the plane wave and the spherical waves associated with it. Now the physics continues. When we solve the boundary value problem, the general solution as r goes to infinity. So the general solution to our boundary value problem will tell me that my overall wave function psi of r, which is a combination of the incoming plane wave plus the scattered plane wave, the whole thing is going to be expressible as some combination of spherical Bessel and Neumann functions. Times which are the following. So what am I going to get when I take the limit as r goes to infinity in this, where I can actually do the matching onto what is the incoming wave and what is the scattered wave? As r goes to infinity, this thing is going to become sum over L, a sub L, sine kr minus L pi over 2 over kr plus BL, not plus, but minus cosine kr minus L pi over 2 over kr times Legendre polynomial. I want to compare this general solution with this one, right? So we said the incoming wave as r goes to infinity looks like that pure sine. The general solution that we will find after including the potential has both a sine and a cosine. I can write the combination of the sine and a cosine as a phase shifted sine. So what I want to do is I want to define this and define my phase shift in such a way that this can be written as sum over L, 2L plus 1, e to the I pi over IL pi over 2, e to the I delta L, which is the phase shift, sine kr minus L pi over 2 plus delta L over kr, EL of cosine theta. So treat this like a definition. In practice, what we will do for specific problems with specific potentials is we will impose the boundary conditions and we will exactly figure out what A and B have to be, to be able to combine this sine and that cosine using the trig addition formulas into a single sine with a shifted coefficient here. So treat this thing as a definition of the phase shift delta. The important part is how it enters into the shift of the sine wave. It's usually defined with this prefactor e to the I delta sub L to make sure that the incoming spherical wave is unmodified. We'll see what that means in just a second. This is just a convention. This is physics. So outgoing wave is a combination of Bessel and Neumann functions, and you can write that as an outgoing sine wave with a phase shift. And the goal of this boundary value problem will be to find the phase shift for a given L. So if this is the general form, I need to use this and match on to what is the scattered wave so I can figure out what is the scattering amplitude. If this is the full wave function, what is the scattered wave? Because I need to pick out what part of that is going to give me the scattering amplitude f of theta. Right, so we said the incoming wave itself already has some incoming spherical waves and some outgoing spherical waves. What I care about is how are the outgoing spherical waves change? That's the part coming from the scattering amplitude. So the easiest way to do that is to explicitly add and subtract the incoming plane wave. So if I write my psi of r equals psi incoming plus psi minus psi incoming. And I write this as r goes to infinity. My incoming wave solution looks like this. I have, let me write e to the I kz plus this answer with this phase shift minus that one. Maybe let me start it over on the other board. So what I get is psi of r is the incoming wave e to the I kz plus sum L equals 0 to infinity. Both of them have the same 2L plus 1. Both of them have the same e to the I L pi over 2 out front. And let's see, so did I just find that one right? I think. Yeah, it's got the 1 over k on it. Okay, great. So I want to match the full solution, which is this one, e to the I delta sub L sine kr minus L pi over 2 plus delta L over kr. Right, that's this piece. And then subtract from that the part that was from the incoming plane wave. The incoming plane wave was, there was a 1 over 2ik e to the I kr over r minus e to the minus I kr minus L pi over r. E sub L of cosine theta, and I think I need to put my bracket here. Yes, because this one had already absorbed the e to the I L pi over 2. So I just want to simplify this bracket here. So bracket equals, I have e to the I L pi over 2, e to the I delta L over kr. That sine function I write as e to the I kr minus L pi over 2 plus phase shift minus e to the minus I kr minus L pi over 2 plus phase shift divided by 2i. And I want to subtract from that 1 over 2ik e to the I kr over r minus e to the minus I kr minus L pi over r. Okay, so let's simplify things here. So that difference is equal to, so if I expand this thing out, so just like before, I distribute the I to the I L pi over 2, that cancels this one, it adds on to that one. Similarly, I distribute the e to the I delta, it adds on to this one and it cancels that one. So I get 1 over 2i kr. After simplifying the phases, I have e to the I kr, and then I cancel the L pi over 2, and then I add the delta. So it's e to the I kr plus 2 delta sub L, minus, in the second term, I add the L pi over 2, and I cancel the delta L. E to the minus I kr minus L pi. And I'm subtracting this with, let me pull out the factor of r, 2i kr. And what's left is e to the I kr minus e to the minus I kr minus L pi. Okay, so the purpose of including that extra delta L in front is to ensure this cancellation. So by construction, yes, there's minus here and then minus minus plus. This was the incoming spherical wave. This is the outgoing spherical wave. So the purpose of including that phase shift here is so that the incoming spherical wave is not modified by the potential. Only the outgoing spherical wave is modified. So incoming spherical wave not modified. And the effect of the potential is to generate a phase shifted outgoing wave. So if I simplify the rest of this, I have 1 over 2i kr e to the I kr plus 2 delta sub L minus e to the I kr. The e to the I kr is common to everything, so I can write this as 1 over 2ik e to the I, 2 delta sub L minus 1 e to the I kr over r. So that was the purpose of setting up the brackets this way. And that gives us the matching of our general solution with the phase shift onto the boundary conditions at infinity. So what we find is that psi of r, as r goes to infinity, is the incoming plane wave e to the I kz plus this correction, plus sum L equals 0 to infinity, 2L plus 1. The brackets simplified to e to the I, 2 delta sub L minus 1 over 2ik e sub L of cosine theta times the spherical wave e to the I kr over r. Okay, this was the point of this exercise. because now I can identify this object as the scattering amplitude. This was the incoming plane wave. We've successfully extracted the outgoing spherical wave from it, and what's left relates the scattering amplitude to the phase shift of a particular angular momentum mode L. So this object is scattering amplitude F of theta. And so what we found is that F of theta is sum L equals 0 to infinity, 2L plus 1. The specific coefficient is e to the I, 2 delta L minus 1 over 2ik, L of cosine theta. You can always take the scattering amplitude and decompose it in terms of Legendre polynomials. The point of this exercise was to figure out that coefficient of the Legendre polynomial is related to the phase shift. So another way to say this is, if I know the phase shifts, I know the entire scattering amplitude, and vice versa. Knowledge of all phase shifts delta L is equivalent to knowledge of the scattering amplitude. Okay, the last step in the process is then to relate this. Yes, e to the I, 2 delta L minus 1 over 2ik, 2L plus 1 kilo cosine. Okay, so this coefficient is sometimes called the amplitude of the partial wave. So A sub L, which is this e to the I, 2 delta L minus 1 over 2ik. And I can write this as e to the I delta sub L, let's say, over k, e to the I delta L minus e to the minus I delta L over 2i, which is just e to the I delta L sine delta L over k. This is the amplitude of the partial wave. So one has f of theta is sum over L, 2L plus 1, partial wave amplitude times Legendre polynomial with A sub L equals e to the I delta sine delta over k. If I know the scattering amplitude, then I can use this to write down the cross section. So in terms of this, the total cross section is the integral over all solid angles. So this is integral 0 to 2 pi d phi, integral d cosine theta from minus 1 to plus 1, f of theta squared. Since in this case, our scattering amplitude is azimuthally symmetric, the phi integration automatically gives me a 2 pi. And I have to take this expression and square it. So I get 2 pi sum over L and L prime. I've got two sets of coefficients, 2L plus 1, 2L prime plus 1. Now I have the two coefficients. Let me write this as AL prime star AL. Integral d cosine theta from minus 1 to 1. EL prime of cosine theta, EL of cosine theta. This integral is, again, the inner product over the Legendre polynomial. So this gives me a Kronecker delta because the Legendre polynomials are orthogonal. So this object gives me 2 over 2L plus 1 Kronecker delta, L prime. This is another way of saying that the contribution to the cross-section from each L is independent. So instead of getting two sums that talk to each other, I get one sum that does not. So sigma total is sum L equals 0 to infinity. I had 2 pi, and I get 2 over 2L plus 1. That cancels one of these factors. So I get 4 pi over 2L plus 1. 4 pi times 2L plus 1. And now if L is equal to L prime, I just get A sub L absolute value squared. And A sub L was e to the I delta sine delta over K. So I get sum over L, 4 pi 2L plus 1. This is absolute value, e to the I delta sine delta over K. Absolute value of the pure phase is 1. And I just get sum over L, 4 pi 2L plus 1 over K squared sine squared delta sub L. What this is telling me is that the total cross-section is built out of independent contributions, partial cross-sections from each value of L. Sum over L, sigma L, where this is the partial cross-section. Of the Lth mode. This is another way of saying that each L scatters independently, each L has its own cross-section. Each L scatters independently. Or the contribution of each L to the total cross-section is sigma L equals 4 pi over K squared 2L plus 1 sine squared delta L. So all of this is a way of defining what is the phase shift. If I solve the boundary problem, how do I find the phase shift? How do I find what each L mode is doing? If I have a problem where only the lowest L modes contribute, then I can calculate this piece for L equals 0, the S wave scattering. And this will make the dominant contribution to the cross-section. So I guess the important part is that for low energy scattering, K goes to 0. We argued this before, but we will see it explicitly with specific examples next time. If K is going to 0, then that means delta L goes to 0 faster for higher L. So for the specific case of the hard sphere that we will deal with next time, we will get that power counting explicitly. We get delta L is proportional to negative K R naught to the power 2L plus 1 as K goes to 0. This is for the case of the hard sphere potential. So you see, as K goes to 0, the higher the L, the higher the power of K, the faster it goes to 0. So this is telling you that the phase shift delta 0 is the biggest, delta 1 is much smaller than that, delta 2 is much smaller than that, and on down the line. Likewise, that means that the partial cross-section, sigma 0, is much bigger than sigma 1, is much bigger than sigma 2, and on down the line. This is the hierarchy that makes this thing useful for low energy scattering. You can get away with calculating just the S wave scattering, or just the S wave and the P wave scattering. And because each higher order thing is small, you are justified in throwing it away. So the point of all of this is that you can solve specific boundary problems for specific potentials. Solve boundary value problems for specific potentials and then truncate or approximate with L equals 0 or L equals 1 and so on. So one has the approximation sigma total. If each one of these things is successively smaller, then the total cross-section is dominated by the S wave. Sigma total is approximately sigma 0, the S wave scattering. for low energy scattering. Okay. We are out of time, but I guess depending on what the class wants to do for the next 2 weeks, we should continue this discussion next week. I would like to finish this off on Monday, and then depending on what comes after that, we could potentially just practice some problems over things that we've already done, or we could continue on from there to discuss identical particles and other special topics that will be needed before the comprehensive exam. Okay, I know this was fast. I know there was a lot of information about special functions that is very specialized. Any questions or concerns about this?
Does this mean that the scattered waves will be in ranges? For example, for L0, the middle, and L1, L2.
Yeah, it means that they will be modulated with that particular angular distribution. So it will generate a particular interference pattern. So as k goes to 0, if this S wave scattering is the dominant piece, then you will see isotropic scattering fringes, if you like. If you have L equals 1, then you'll see the particular like P wave modulation. So I think the answer is yes. If you have a superposition of many such modes, then you can get an interference pattern out of them that becomes more complicated.
Scattered will not be uniform distribution.
That's right. But if you go to low enough energies, it will always become uniform.
Because this one is the dominant.
Because the S wave is the dominant. Exactly. And so the physics of that is that at low enough energies, the wavelength of the scattering particle is so long, it cannot see the details inside the target. It only sees a hard sphere, essentially, with a particular size. So one consequence out of this is that that S wave scattering basically just has one number that characterizes it, which is called the scattering length, which is basically the radius of a hard sphere that you're effectively bouncing off of when your wavelength is so long that you cannot see inside the target. And only if you have high enough energies that you can see inside the target do you actually generate complicated interference. Other questions? All right, if not, thank you for your patience. If you have not already done so, please go to Canvas as soon as possible and weigh in on what you want to do for the second midterm. That will inform what I do for the next couple of weeks, and I need to make that decision in the next day or two. Thank you guys very much. Have a nice weekend.